Fantastic. Okay, good morning, everybody, and welcome to this last week of the Acer's tutorial on the Bayesian optimization of automated experiment. So today we are going to dig deeper in the deep kernel learning and how to select the experimental setting for the DKL, how to make the DKL explainable, and how and why realize human-in-the-loop intervention. So before we go into the DKL details, let me start with the kind of the reminder of what the Bayesian optimization is. So all of you have seen this slide by now, probably many times. So, but it's important to keep it in mind because once we are going to go through the rest of the lecture, we are going to reassess and learn how to apply the Bayesian optimization methods for the real world problems. So by now you already have this magic mantra of how the BO works. We do some type of measurement. We show the example of the some functions defined in the 1D space, and the function itself is a scalar, so it's the simplest function in the R1. We do measurements. Based on measurements, we reconstruct the function and we reconstruct the uncertainty. Then we create the acquisition function or policy that somehow balances the prediction and uncertainty. We take the next measurement at the location where there is a maximum of the acquisition function. We recalculate the function, we can recalculate uncertainty, and then we proceed until we run out of the experimental budget. So we discussed that the policy can be greedy. Greedy means that you go for maximum of the prediction. The policy can be exploratory. That means that you try to minimize uncertainty. The policy can balance prediction and uncertainty depending on how much time we have and what we want to explore. So by now you, and the simple 1D Gaussian processes basically allows us to realize it. Now, there are several important things that we want to look in detail, which are absolutely essential when we think about the application of these methods in the real world setting. So first of all, as we discussed, this x-axis can be considerably more complex than just one-dimensional parameter space. So if we go from 1D parameter space to 2D or 3D, that's not a super big difference. So Bayesian optimization in 4-dimensional parameter space, if the parameters are continuous, is not that different from optimization in the 1-dimensional space. It's just more difficult to visualize it. The difficulties appear if our parameter space has a completely different nature. For example, formally, the space of the processing trajectories is infinite dimension. It's not one dimension. So we need some way to work with these high dimensional spaces. Same applies to the molecular spaces. So molecular descriptor is a very high dimensional object. Same applies for building structure property relationship. Structures are very high dimensional objects, and so on and so forth. So this is very important, but very often the space over which the function is defined is basically something coming from your specific business problem. So in some sense, you don't get to choose the space in which you operate. If you do process optimization, like pressure, temperature, whatever, you have low dimensional search spaces. If you want to optimize the battery charging, you need to work with the high dimensional spaces or learn how to represent them as low dimensional. If you want to work on molecular discovery, so in some sense, the space comes from your business case. But the part which is a little bit more complicated and requires a lot of thinking is this optimization function. So optimization function is clear if and only if you have a specific problem where you essentially know what is that you need to optimize. For example, the conductivity of the electrolyte, or you need to optimize the density of the band gap of material, or some other physical parameter that is immediately measurable during the experiment. The problem is that the reward function, so something that we want to optimize, is not always straightforward. And there is a tremendous amount of the business problem when we actually need to come up with one. So this is a very common problem for machine learning. In fact, one of the factors that limits the application of the machine learning in the real world environment more than anything else is actually this problem with how we select the reward functions. So for experiment, we typically know objectives. What is the ultimate goal of the experiment? Problem is that the objective is not something that we get access immediately. We get only something that supposedly allows us to approach it. So generally, for the time being, there is no consistent frameworks for the selection of the reward function. So people just start thinking about it. So beyond the immediate optimization goals. However, in certain cases, it is possible to take the applications of the Bayesian optimization that we already have and make this connection between the Bayesian optimization and the reward explicitly clear. So what I'm going to do is first to illustrate how it is done in imaging, because this is the area where, relatively speaking, my group has the biggest experience. And then in the next lecture, we are going to talk about how it is going to work for the scenarios when we have multiple experimental tools operating at the same time. And the reason why it would be important for the multiple tools is because imagine that you want ultimately, we have an automated lab, right? So that's by now is doable. We can actually buy those. They are not even that expensive. If we want a machine learning agent operate the automated lab, that means that machine learning agent needs to issue commands to multiple tools. But this is possible if and only if we somehow have a strategy of how we balance what we learn or balance the value of what we learn from the different tools. So how does the knowledge of the X-ray data help us understand the Raman data? How does the knowledge of the atom probe tomography of the sample help us make sense out of the, for example, mechanical testing? These things are very non-trivial, and this is purely a domain area. So this is not something that folks working in the classical Bayesian optimization can do. So the closest area here would be something like supply and chain optimization, but then there everything is measured in time and money. Scientific world, our measures of success are different. So with this being said, let me illustrate some of the simple examples of the Bayesian optimization and show how they, what the reward functions are. So the simplest example is imaging. So imaging optimization. So for example, by now there are about 100,000 atomic force microscopes in the world. So all of them are human controlled. There are special cases with some of the nanoserve machines that are part of the manufacturing lines in industry, but by far and large, AFMs are relatively cheap benchtop tools. That means that each time there is an instrument collecting data, there is somebody sitting in front of it and actually turns the knobs in order to make sure that the microscope works. So the most basic form of imaging in AFM is topographic imaging. You essentially want to scan the sample and get the profile. So we have a certain parameter space. So we have the set point, how hard we push on our cantilever. We have a driving voltage, how much bias we apply to excite the cantilever. There are other parameters like different form of gains in the feedback loop. So if we take these parameters together, then parameter space for imaging is very well defined. This is just about 5 to 6 dimensional parameter space, and each person running AFM starts the morning with actually finding out the right place in this parameter space to run the experiment. And the signatures of the microscope behaving well or not so well is actually reasonably known. So for example, this is an example of the AFM working just right. You see that the the orange line and blue line coincide. That means that the trace and retrace coincide. And our phase signal is stuck around certain value and shows some variations kind of closely related to the topographic changes. We know that if we try to be too gentle, then the trace and retries don't coincide. So in this regime, we are very gentle, so we don't destroy the sample and the surface, but at the same time, we don't get a good topographic scanning as well. So this is what happens if we push too hard. So in this case, we still have a decent topographic scanning. We start missing some details, and also our face start to behave somewhat poorly. So each person who runs AFM essentially tries to find the optimal condition that should look like this. So can we use machine learning or Bayesian optimization actually to make the microscope optimize the scanning by itself? The interesting part that from the point of view of the Bayesian optimization, this is not super difficult. So Bayesian optimization in the 5-dimensional space is actually a straightforward problem. The difficult part here is to define the reward function that somehow can represent this behavior of the curves in a way that allows us to create a single parameter that we want to optimize. That part is actually very difficult because the quality of scanning would be different depending on what type of sample we are looking at, right? So for this particular sample, topography looks this way. For other sample, the topography will look that way. So actually, it turns out that in this particular case, the secret sauce is actually the reward function. And the difficulty here is that the human somehow can always recognize, after spending some time running the microscope, what is good and what is not good. Creating the reward function that kind of imitates the human will provide the same outcomes or close outcomes to the human operator ended up being something to be very, very difficult. So that's something that took us quite a while to develop. And there is a lot of human heuristic and know-how that went into making it work. However, once the reward function is defined, everything else is actually straightforward. Then we can explore our parameter space. We create our predicted reward function, our acquisition function. This is the typical way how the optimization works. So we started with some initial seed values of the in our parameter space. Then the microscope worked for several iterations, and then it discovered the optimum inside the parameter space of the microscope optimization. So this shows for this optimization for the 2D case. It doesn't have to be it doesn't have to be two-dimensional. It can be considerably more complicated than that. It's supposed to be a movie and work, but somehow it didn't work. But it's possible. So the point is that the reason I'm showing you this example is that in many cases, human develop some form of heuristic feeling about what is good and what is not good. Translating this into the language of the function to be optimized is very difficult. On the other hand, once it is done, then a lot of problems that used to be heavily biased and human dependent become a simple optimization problem. So that's one example when, and by the way, in atomically resolved imaging, whether it is scanning tunneling microscopy or electron microscopy, relatively speaking, optimization of imaging is much easier. And the reason for that once you have access to the atomic structure, once a part of the imaging, it's very easy to judge the quality of the image based on the Fourier transform. All we have to do is to look on the position of the peak in the Fourier transform, which is visible. And that gives us the information limit of the technique. So basically, optimizing the Fourier transform to have the peaks clearer is much easier task than optimizing the non-atomic resolution imaging. So from that perspective, we can expect that the automated image optimization in STM and electron microscopy will become a thing very fast. In AFM, I expect that there would be some interesting developments of how people develop the suitable reward functions to make it happen. So another example, physical law discovery. So physical law discovery sounds like a reasonably abstract reward function, But interestingly for us, that's exactly what the hypothesis learning and structured Gaussian processes do. Simply because we define the knowledge of physics, we equate it with essentially knowing this symbolic model for our process. This is actually something that, from the point of view of the Bayesian optimization, is relatively straightforward. I've shown you an example that if we have the instrument with the Python API and we have a well-defined experiment, we can actually relatively straightforwardly run the workflow when the instrument learns by itself what are the laws that describe the ferroelectric domain propagation under the action of the bias pulse of some amplitude and time. So in this case, the reward function is very well defined. It is the minimization of the uncertainty of the physical model. So we need to choose the beta model out of 4 or the larger number of models, and we need to find the parameters, and that's our reward. So we run out the experiment to maximize the physics knowledge. So the question becomes, when is it possible, when it is impossible? So in order to do something, we cannot get nothing out of nothing. So the pure data methods minimize the predictive uncertainty. So the measure of the quality of the reconstruction of the function from the data only in the predictive uncertainty over the whole parameter space. With the structured Gaussian processes, this is the posteriors of our parameter values and the chosen model. So that's our reward in this case. So for images, situation can be totally different. So again, image analysis or analysis of any other type of data very much depends on context. So we cannot create a workflow that will analyze image for all possible scenarios. Ultimately, it all depends on what is that we want to learn. So let me show you one of very recent example of how we can use the Bayesian optimization for the image analysis. Imagine this is the image. For those of you familiar with the high temperature superconductors, so this is the prototypical yttrium barium copper oxide, so 123 cuprate. So you can clearly see the electron microscope shows you the essentially all the major building blocks of the material. If you look at it, you can see that in some places you can see the sublattices corresponding to the second type of atom actually become, these layers actually become disordered. So what's going on? So what goes on is that this material was irradiated, and the radiation introduced the weak damage on some of the sublattices. So we can see the strong atoms, but not the weak atoms. So the question becomes, can we analyze this image and find the atoms in it using simple models and ideally find the sublattices, find the amorphous regions? So normally, this type of image analysis problem is absolutely not an optimization problem. So normally people generally analyze this type of workflows manually, and essentially they try to go from step to step, go forward and backward. So generally analysis of the data like this very often takes days and weeks, even from the qualified operator. So it turns out that if we manage to create the reward functions correctly, we can use Bayesian optimization in order to do that. So I haven't talked about the multi-objective optimization, but that's basically Bayesian optimization when you try to reconstruct two functions rather than one, improve two functions rather than one. And it turns out that if we can create the reward functions, then we can represent the analysis problem as the optimization problem. And if we present the analysis problem as an optimization problem, that means that we take the human out of the loop. We actually can get the machine learning algorithm to do it for us. How we can do that? That's a difficult part. So for example, for this image analysis, we started with the very simple physical criteria, saying that, you know what, when I look at the image, I know my field of view. I know that this is a crystalline material, which basically means that I can estimate what should be the total number of atoms inside this image. I also know that if I try to, let's say, optimize the number of atoms, try to find them as many as possible, then my algorithm will start to create false positive. It's actually not very difficult to accomplish. So the second criterion I want to introduce is to create that we should not have the false positive, meaning that if we find atoms, they should be all at certain distance from each other. So they cannot be closer than the minimum of atomic distance in this material. So if I define these two physical criteria, then I can take a very simple image analysis function, what is called the Laplacian of the Gaussian, which has the several control parameters. So if you look at the scikit image, you will get the direct exact description. So basically what I do is that I say that, you know what, there are 4 parameters that define even simple Laplacian of Gaussian. So I can do it manually, but then there are kind of additional elements in how you smooth the function, and the image, and so on and so forth. But another approach I can do is that rather than trying to tune the parameters of this function manually, I can introduce this reward function that come from the physics of the problem, and then I can simply run the Pareto frontier that finds the best way to best parameters. So in this case, the Pareto frontier is actually done in the 4-dimensional parameter space. So this is our optimization space. We visualize how well we can achieve the first objective and the second objective. And that tells us that this is how good it can get. So there is always give or take. So we, at some point, we get one, but not the other. And we can benchmark it using the deep convolutional network. So the DCNN works very well on this type of data sets. So it allows us to check whether the answer made sense or not. So why do we want to do it by the log or optimized log rather than DCNN? Very simple answer. DCNN is a supervised machine learning method. We need to train it, and we need to train it given the label data. So there is a tremendous amount of time and effort into preparing the training data. Secondly, DCNN is very sensitive to the out-of-distribution drift effect. So if our parameters change, the DCNN trained by one sampling or resolution will not very well work for another one. And third reason, there is such thing as a computational complexity. So DCNNs are usually fairly heavy algorithms. Electron microscopes generate the data very, very fast. So having the DCNN deployed as the part of the image analysis workflow comes with some amount of investment. So optimization of the logarithm of the Gaussian, relatively speaking, is a very light algorithm. It is just a simple image analysis combined with the optimization loop. So there are scenarios where using the light optimized algorithm is much better proposition than using the deep convolutional network. It doesn't mean that the optimization is better. It means that there are cases when it is more useful. So for example, if we were looking for much more complex objects than the atoms, then DCNN would work, but something like this wouldn't. So, but it's good. So it's good to have both options. Turns out that the reward function approach can be actually extended to much more complex analysis workflows. So imagine that now, rather than finding atoms, I want to find the amorphous regions inside the material. So classically, the way that this type of data is processed is through the workflows like this. So I show only 4 steps, but practically it can be much more, up to 12, and then humans cannot do it anymore. So the way it's done is you start with the image. Then you create the descriptors. So the descriptor is typically one way to create them is to find the atoms and then define an image patch based with the center based on the atom. So the descriptor will have a size and shape. So the size can be essentially the window size, but it can also be rectangular. Then we have 2 sizes. It can be a circle. It can be an ellipse. So there is a considerable parameter spaces associated with the choice of descriptor. Then we need to choose what to do with the descriptor. So we can leave it as it is. We can apply the Radon transform, which allows us to find straight lines. We can use Fourier transform that allows us to find periodicities. Then we feed our descriptors into certain clustering or dimensionality reduction algorithm. So it can be anything, GMM, PCA, NMF, whatever. And then we get some form of the descriptive statistics. So in this case, I've shown a simple workflow. Practically, we very often will do the clustering in order to separate the clusters in the different atomic types. And then we will explore clusters one by one. So it actually can get to 5, 10 steps very easily. What's the problem? The problem that in this case, the reward is actually non-myopic. So for example, if I want to find the amorphous regions, I can come up with an algorithm based on something like PCA plus the variational autoencoder that will take an image like this, or to be more specifically, the original image here, and represent it as something like this. So if we do so, then we are going to see the indicator that we were kind of getting close to that. So we see the regions that show different contrast. We can argue that maybe this is an amorphous region, but then we see a lot of other variation within the data. The problem that in this case, the workflow like this requires the human oversight on each step because each of those parameters comes with the control variables. So GMM comes with the way how you can represent your covariance matrix. NMF comes with the number of components and so on and so forth. And the problem is that the reward in this case is non-myopic, meaning that quality of the image that I get in the end depends on the decisions that I made fairly early on in the analysis workflows. As the result, if I want to analyze the data like this, I basically have to go forward and backward and experiment. And as you can imagine, if you have multiple steps, sometime analysis takes 10 minutes if the image is sufficiently large. That becomes really complicated really fast. So it turns out that, again, this type of workflows can be automated using the Bayesian optimization. What is the key for getting it done? The key is to define the reward function. And in this particular case, we say that, you know what, ultimately what we want to do is to discover the amorphous regions. From the general physics sense, we assume that there are several characteristics about it. First of all, it has to be some difference between the atomic neighborhood just for one atom site. So it's a binary classification problem. Notice that it's unsupervised binary classification problem. Secondly, we assume that these amorphous regions have to be compact, meaning that they form kind of clusters. We don't expect them to see like snowflakes or whatever. And the third is that we want to minimize the perimeter of this so that they are kind of look more like droplets rather than extended regions. So, and then it turns out that in this case, again, if we define our rewards, then everything else becomes relatively straightforward. We define our workflows. In this case, we also experimented with something light. So we have a parameter space where one parameter is the window size, another is the threshold, third is the covariance type. So two parameters are continuous, one is categorical, but then we find a way to use the Bayesian optimization to actually separate the amorphous versus non-amorphous materials. And notice that this is a classification in a very high dimensional space because our object is actually a patch. The number which has a dimensionality of, let's say if it is 30 by 30 pixel, dimensionality is 900. So this representation is not of the object itself, it's their projection on the two-dimensional space versus via the principal component analysis. But the number of ways how we can classify in the 900-dimensional space is extreme. So we obviously have multiple ways to separate the data. Using the Bayesian optimization with the defined reward function, we find a somewhat non-obvious way that allows us to actually do it in such ways to get the best behaving clusters. Again, the Bayesian optimization part is actually not that difficult. The difficult part is definition of the reward functions, because they have to be obtained from physics and not from something else. So I've shown you the toy models, but it doesn't have to be the toy model. Essentially, any linear workflow, no matter how many steps, can be optimized this way. So the more steps, the higher is the joint dimension of the parameter space. But the current optimization libraries can do exceptionally well even in a very high dimensional spaces. Something like 100 is doable, and you can have optimization when some of your parameters are continuous, some of them are categorical, and so on and so forth. So this is a super powerful part. This is where Bayesian optimization gives you results. Catch, define your objectives. If the objective defined correctly, things work. If objectives defined incorrectly, you can have a reward hacking, and then things are not going to work out. Does it work for imaging? So I've shown you the example that if we try to use the Bayesian optimization just for imaging, meaning to learn the black box function of the image contrast from the measurements, that actually does not work well at all. So in this case, we can get the results which are look like they're plausible, but ultimately they don't tell us much compared to the ground truth measurements. And the reason why it doesn't work in this case is simply because our ground truth function is very complicated. So the images tend to have details on multiple length scales. And in this case, the Bayesian optimization doesn't work very well. That being said, it is a useful exercise to define what is our reward function in this case. And the reward function in this case is the minimization of the predictive uncertainty. So what it means is that the algorithm has a prediction of what should be the contrast at each point based on the measurements done only in the selected points. So in this case, that's the measure of success, and the method didn't work very well, but at least we know what we were trying to accomplish. So that's already a good start. So with this being said, do you have any questions about the reward function? Because ultimately that would be the most important aspect of the application of the Bayesian BO in the real world environments. So any questions on this one? Okay. So if no questions, then let's kind of recap the case of the go back to the case of the deep kernel learning and recap why the deep kernel learning is necessary in the first place. So all the examples that I've shown you so far operate only in the low dimensional spaces. So now we are going back to the discussion of the space over which the algorithm operates as opposed to the reward function. So we assume that the correlations are defined by the kernel function. We don't use any knowledge about the physics of the system, of course, unless we use the structured Gaussian process. We don't use cheap information available during the process. So what can we do to explore the high dimensional spaces? So what can we do to explore the high dimensional spaces? So let's look at the examples where the exploration of the high dimensional spaces becomes important. And again, I will show this example for microscopy, but the same considerations apply into a lot of real world problems. For example, if you want to optimize the property of the battery based on the optical images of the cathode material, you will have exactly the same problem. If you want to optimize the mechanical properties of the polymer or behavior of the transport property of the membrane in the electrolyzer based on the microstructures, again, it would be the same problem. And even in imaging, I'm going to show the examples for the scanning tunneling microscopy and variants of scanning probe and electron microscopy. But again, in imaging, it is also much more general than that. So in all these problems, we typically have the access to two characteristics. One is structural imaging, which is chip, which can be topography in STM, amplitude phase in AFM, HUD image in electron microscopy, and so on. The important thing is that these are fast and come with a large number of the structural detail. We also have functional images, which are expensive. So in the STM, it is spectroscopy. In PFM, it's polarization loop measurement. In STEM, it's SILS. So those can be either slow or expensive or destructive. For example, if we want to use the non-indentation on complex microstructures, if we do a measurement in one location, we cannot make any measurements in the adjacent location because there is a huge hole in the material. Sometimes the measurements would be kind of non-destructive per se, but simply doing measurements for a long time results in the accumulation of the damage to either the probe or the material. So not to mention that measurements take time. So the question, as I mentioned, this applies to imaging. The same logic will apply for the case when this is an imaging. And this, for example, is measurement of the functional properties, like a battery testing or something like that. So what type of problems do we have? So one problem is that we look at the image based on our domain experience or curiosity or some sampling strategy. We choose the locations where to take the detailed measurements of the specific property. So for example, here you can see the example of the measurements done in the hole, this type of hole and this type of hole in the STM image, and you can see that the spectra are very different. How do we select the locations? So we can do it based on the operator experience. So somehow we know that these are more important than this. We can do it based on the curiosity. So we say that we have this type of microstructures, this type of microstructures, this type of microstructures. Let's sample all of them just once. But in all cases, whether we sample based on the prior knowledge or based on the curiosity or statistical representation objects in the system, we make decision based on what we observe in the chip image in order to select locations for the expensive measurements. So the assumption is that we cannot take expensive measurements everywhere. However, there is the inverse problem. So the inverse problem is that imagine that we would like to discover what regions have, for example, this type of behavior. So for whatever reason that are related to our business case, we want to find out which locations or which microstructures maximize the position of the intensity of this case bosonic peak. So the reasons why we want to do that are up to us as the domain expert. We may have the prior knowledge that tells us that this is important. We may be interested in find the variability of the behavior. So that's not something that Bayesian optimization or any machine learning can do for us. What it can do is to help us discover this material space in such a way as we try to find out where these regions are maximum. So how can we do that? So in order to do that, and this is this kind of the same example of the same logic applied for the EELS measurements, where we look at the structures observed in the electron microscope. We can take the spectroscopy, so in this case, it is EELS rather than STM, STS, and we want to, for example, find out which microstructures optimize this specific loop. So this is the case where the deep kernel learning comes into play. And we went through it quickly in the end of the previous section on last Wednesday. So let's look at it one more time to make sure that all the elements are in place and that we use these elements in order to build the foundation for the human in the loop intervention. So we describe both how human can intervene in the process and why humans can intervene in the process. So where do we start? We start, in imaging at least, with the acquiring the full image and splitting it into the image patches. So the reason why we do it is because we simply say that we believe that it is only the local structure that relates to the property. So in other words, the peak, that the spectrum that is acquired here will be affected by the structure here, but not by the structure here. So that implicitly means that our interactions in the system have to be short-ranged. So there are, of course, the exceptions, but there are not that many exceptions, so we are good. How does the same approach applies for for example, process optimization? In those cases, it is natural. So in the process optimization, one trajectory produces the outcome that would be dependent on this trajectory, but not any other trajectory. So this assumption holds exceptionally well. How does it apply for molecular discovery? Exactly the same way. So there is no internal logic or arrangement between the different molecules. Each molecule has its own properties. Only the correlations between the molecular structure are related to correlations between the properties. So in this case, imaging is actually a little bit more complex problem, which basically means that if we solve the problem for imaging, we solve the problem for everything else, which is kind of pleasant. So what do we do next? We need to define our scalarizer. So what scalarizer means is that we measure something. For example, we measure a spectrum, or we measure the 4D stem or Rankigram. We need to define what is that about this spectrum that is of interest for us. So for yield spectrum, this can be the intensity of the certain peak, position of the peak, ratio of the peak. So anything that takes the spectrum and transforms it into the single, or maybe several, if we want to do the multi-objective process, measures of interest. So scalarizer is our reward function. So as I mentioned in the beginning of this lecture, if we want to use Bayesian optimization, we need to pay attention to what is our discovery space and what do we want to optimize. So in this case, our discovery space are the local patches. So these are our local microstructures. And what we want to optimize is the scalarizer function. How does it apply for other systems? So if we want to do the process optimization or the molecular discovery, then our scalarizer is simply the target property that we want to have. So it can be something like a molecular property, or it can be something else. So if we want to discover the molecules that have a specific optical spectrum, so then we also need to figure out what is the spectrum that we are interested in, right? So do we want to maximize the intensity? Do we want to maximize peak position? Or maybe we want to say that, hey, this is some example spectrum, and we want to find the molecule that has the example spectrum, which is as close to this standard in the mean square error as possible. But in all cases, no matter what we do, we need to define the function that we want to optimize. So, and that, again, that is domain specific, and there are multiple ways how it can be done. However, once we define this scalarizer function, no, it's fine, Greg. So once we define this scalarizer function, then the process becomes already something that machine learning can do for us. So how do we do that? So first of all, we need to initialize our model. So the way we do that is we take our exploration space. So it can be several patches. It can be several molecular candidates. It can be several trajectories. We take those special locations and we measure the properties of those locations. So the property has to be a scalarizer function. So we can measure a spectrum and then we calculate it, or we measure the scalarizer directly if we talk about something that can be just directly measured. Once we identify this property, our next step is where the magic happens. So this is where we use our deep kernel learning model, where we take the examples of the pairs between our high dimensional descriptors and our scalarizers, and we train the model based on these examples. So at this stage, it is essentially supervised learning. The thing that is exceptionally important about the deep kernel learning is that this seed step can be very data light. So we really need a very small number of examples to train the algorithm in the way that makes sense, stable, and produces reasonable results. So after we train our model, the next thing that we do is we take our all structural data and we feed it inside the model. So what is going to happen in this case is that for each patch in our patch collection, so in our full image, we will calculate the prediction of the scalarizer and the uncertainty of the scalarizer. And in this case, prediction and uncertainty of the scalarizer is exactly the same thing as the acquisition function, as the elements of the acquisition function and the normal Bayesian optimization. So now for each point where we actually have not measured the properties and we have not calculated the scalarizer, we will have its prediction and the predictive uncertainty. With that in place, all we have to do is to find the argmax. So whether we calculate the acquisition function, we find the argmax of the acquisition function, and that finishes our Bayesian loop. What's interesting, and I kind of observed it for many other problems, is that ultimately deep kernel learning for microscopy is probably the most complex example compared to other applications. So relatively speaking, the data itself is simpler because the structural descriptors are relatively simpler than molecular descriptors or process optimization descriptors. But the number of things that you need to keep a track while doing the decal on imaging is, relatively speaking, larger than if you do it for process optimization or for molecular discovery, which basically means that if you figure out how it works for imaging, it is relatively straightforward to apply it for other cases. So if we bring it all together, then this is how our deep kernel learning-based Bayesian optimization workflow looks like. So we start with our structural data. If you will, structural data is equivalent to defining our search space, where each object in the search space is the image patch taken from specific location. So molecular discovery, process optimization, it is just the complex objects. They don't have a specific location. Then we measure a spectrum and define a scalarizer. So this part is equivalent to take a physical measurement and then tell what is that we're interested in. So this is where we form our reward function. Then we train our deep kernel learning model. Then we get our acquisition function. So this is the second decision that we make, how we balance exploration and exploitation. Then we decide next position. So this is the workflow. I've shown you the examples of how it works in the real world. So if we take the sample with the different Hill spectrum, if we define our scalarizer at the ratio of peak number 2 to peak number 1, so this is the bulk plasmon, this is the surface plasmon, this is how it works on the electron microscope. So this is the example done at Oak Ridge about 2 years ago. Now we can run the same type of workflows on the Thermo Fisher Spectra at University of Tennessee. Generally, if you have the instrument which have the Python interface, whether if you have geols, then it's PyGem. If you have the neons, it's Swift. If you have the Thermo Fisher, then it's AutoScript. So basically, all of the microscopes with the Python API would be able to support this type of workflow. So at this point, it's relatively straightforward. So 3 years ago, we've done it on the Neon because they have Swift interface, and at that time, other microscopes available to us didn't. So that actually predicated the choice of the system for deployment. So look what happened here. Once we run this workflow, you can see that our algorithm has discovered these regions, which is good. But here is something that should be a yellow flag, meaning that why does it discover this edge but not this edge? So that being said, the important thing, it worked, and it worked exactly how we promised it will work. So what happens if we look at the different samples? So again, So this is the one that I've shown you. This is another example. So you see that the locations are selected here. This one, it kind of explored everywhere in the edge. This one, it chose this edge, but not this edge. And this becomes a very interesting question, and that leads us to the whole concept of the human in the loop and the explainability. So when the automated experiment works, it's great. And it gives us results that presumably tells us something about the physics of the experiment. But the natural question is, why did the automated experiment run that way? So when we deal with the imaging data, it's very easy to pose this question because the images have the internal structure. We can see that this is this edge is discovered, this edge is not discovered. So this question is natural. But the same type of questions can appear if we explore molecular or process spaces. Again, these are large exploration spaces. It's a reasonable question, why did we explore this molecule? And why didn't we pay attention to this molecule where structure is actually very close? So can it work for other modalities? And what type of questions we have? So yes, we can run it for other modes. For example, for 4D STEM, we run through the same protocol. So we need to define our scalarizer function, which is typically some simple derivative of the 4D STEM dataset. So we can either run automated experiment when we take the data stream from the instrument, find all the atoms, and then we choose where we want to measure for this stem. So we know atomic structure, we choose the locations where to measure it, or we can choose to run the inverse experiment when we go through the deep kernel learning. We measure ronchigram, we define the scalarizer, what is it that we want to discover, then we train the decal model, and then we run the same workflow. So forward and backwards, same for EELS. And I've shown you the example of how we can simulate it on the data and kind of simulate the discovery path. But when we run it on this, even when we run it on the simulated data, we can see that sometimes something weird happens. For example, on this example, you can see that the measurements are clearly stuck in this location. So we sampled this region much more than we sampled all other regions. So you can say maybe there is something interesting here, is just the coincidence that it's on the edge of the sample, but here it clearly starts to explore the hole in the center. So the measurements are being, measurement budget is spent between this location and this location. And the same type of things happens if we run the measurements on the active instrument. So this is not a simulation anymore. This is the algorithm running on the active tool. So notice that it got stuck on this location. It actually did a decent job sampling everywhere on the material surface. It definitely got idea about what happens in these locations, what happened in these locations, but then it got stuck. So first question is why? And second question, what are we going to do about it? So this is just the same data set, but showing the different steps of the process. So you can see that exploration starts here, then we go to the broader exploratory phase, and then the acquisition function start to have maximum over here, and we are not going to get out of this until we explore all these high visibility points. So notice that once this acquisition function formed, then we expect that the prediction has maximum over here. The uncertainty has maximum over here, has a maximum over here. So in some sense, we got stuck in this location because here the uncertainty was highest, so the algorithm could not predict very well. But we got stuck here because here the prediction was the highest. And if we look at this data, it is very easy to say that, hey, there are ways to solve this problem. So if we know that we can get stuck in the one location, we can simply introduce the penalty term for doing the measurement close to the previous measurement. And we can let this penalty term to anneal out with the time. So it's actually a very easy thing to do. We just need to introduce some Gaussian, which we subtract from the acquisition function. So we will penalize the point where we took the measurement. So the next time, if we do the measurement close, we penalize it more. With time, this penalty will anneal out, so we don't have to deal with that. And in some sense, experimenting with the different ways how we can combine the spatial uniform or space exploration inside the image space and the acquisition function, that's actually a very useful way of adapting these workflows for the imaging. For molecular spaces or processing spaces, these approaches don't work unless we have some measure of proximity in those spaces. So then we can penalize the processes or molecules that were close to those that we explored previously. But anyway, question is, we get stuck. Sometimes we get stuck on the cluster. In this case, we can say that, hey, maybe we discovered something interesting. But sometimes we very obviously get stuck in the hole and in the corner of the image. So, and notice that very, very annoyingly, we keep spending most of the time here, and from time to time, we go to explore the other parts of the sample. So that doesn't feel like it's very, very useful. So does it happen in other settings? Yes, it actually works in the scanning probe microscopy as well. It's not limited for the electron microscopy. So if we realize the deep kernel learning on the AFM, for example, for measuring the ferroelectric hysteresis loops, we run exactly the same scheme. So this is how our images look like. This is how our measurements look like. These are the hysteresis loops. This is exactly the same deep kernel learning workflow. In some cases, it works exceptionally well. So this is the example of the deep kernel, probably the first deep kernel learning example, where we tell the microscope, please find the regions where the hysteresis loops, so the hysteresis loops here, have the maximum area if this is when the electric field on. So here what you see is the structure. This is the number of the measurement points. So we have from 0 to 200. So you can see that the exploration started with these locations. And then the microscope discovered that the hysteresis loops are big on these domain walls. And then it basically spent all the experimental budget exploring this ferroelectric domain wall. And this is superb because we know that, but the algorithm does know that it is very plausible for this domain wall to have the high on-field hysteresis loop area because the domain wall can wiggle and the hysteresis loop opens up. If we change the scalarizer, so if we look for the area of the off-field hysteresis loop, then the algorithm discovers a different domain wall. And again, it first explores different parts of the domain, and then it will focus on this specific domain wall, and actually the process converges. So this is definitely a success because in this case, we can explain everything that the algorithm has done, and the algorithm discovery comport to what we think happens in the ferroelectric material. Of course, the question that we need to solve is how do we choose the right channel to learn from? Because typically instruments are multimodal, so we have more than one channel that we want to explore. So for example, in the piezo response measurements, our channels are amplitude, phase, frequency, and topography. So which of those provides us the better prediction of the property? Turns out that we can actually use the same hypothesis learning approach when we try to have different predictive models compete. And in this particular case, you can see that after 500 exploration steps, the blue model actually was the one that provides the lowest uncertainty. So we were able to find out the channel which gives the better prediction, and that one is actually channel 1, which is not surprising. But again, if we run the AFM experiments, very often we come to the situation when the system seems like it's get trapped in the local maxima. So look what happens. This is the experiment when we are looking for the nonlinearity of the hysteresis of the response voltage curve. So for linear piezoelectric, the relationship between the amplitude and the AC voltage would be linear. For real material, it's non-linear because it's non-ideal ferroelectric. There are kind of motion of the domain walls and so on. So what you see here is the exploration trajectory on the PZT sample. So in the beginning, we explore the image plane reasonably well, but after a while, you can see that we start to focus only on this location. This is the similar exploratory trajectory on the magnesium zinc oxide, sorry, hafnia. And in this case, again, we explored a little bit everywhere, and then we start to be stuck only in these two locations. So the question is, what is going on, and what can we do about it? So what is going on is easy to explain both from the, it kind of goes to the question of balancing beliefs, right? So one way to proceed is to say that we absolutely believe in our algorithm, and that means that the automated experiment discovered something new about the physics of this system. That's a being optimist. Realistically, that's not a very good explanation. So we know that most of the time, the machine learning algorithms tends to get trapped in the certain maxima. So in the kind of false maxima, it happens all the time. The problem is that in the active learning experiment, we cannot necessarily diagnose. So when we're running it on the pre-acquired data sets, we can repeat the experiment many, many times, change the parameters, see how the exploratory trajectory is going to change. But if we have the experiment which is real time, we of course have very limited opportunities to go back to the beginning of the experiment. First of all, experiment in real time is expensive. And secondly, because everything changes, the instrument drifts, sample changes, probe changes, and so on and so forth. Which basically means that if we want the automated experiment to be useful, we need to come up with the two things. One is the explainability, and the second is control. So what does it mean? It means that in the conventional experiment or lab workflow, basically a human does everything. Human defines scan parameters, positions the probe, defines the measurement, and so on and so forth. So human simultaneously executes the experiment and human plans the experiment. And the thing is that it's so closely connected that we don't separate the execution and planning from each other. We just do it at the same time without thinking it. It's like perfectly hands-on. In the automated experiment, we define the policies before the experiment, and at least until now, we didn't change them. So we define our scalarizer, we define our balance between the exploration and exploitation. We tell the algorithm to follow this scalarizer and these policies, and then we kind of let the instrument run the experiment, and then in the end, we look at the results. Sometimes it works, but not always. Then the question becomes, how do we explain the progression and how do we control it? And control means that means two things. So control means that we need to have functions that allow us to monitor the active experiment, and that it necessitates having some controls that we can tweak in order to steer it. So we need to have a monitoring and we need to have control. So these two are closely related because explainability in some sense means monitoring. So if we make explainability real time and add the controls, then it becomes controllable. And this is the place where we start to have we find ourselves to be in a very interesting space compared to the majority of the machine learning community, because as I've shown you example of this paper by Nanda de Freitas, which have been 8 years ago, but that was actually the turning point when the domain community started to rediscover Bayesian optimization. The whole idea coming from folks like Shahriari or de Freitas, so the pure theorists, is that we need to take the human out of the loop completely. So this is sometimes can be a problem. So remember that a few months ago, there was several months when there was exceptionally active discussion of the AI risks, X risk, whatever. So some of this discussion was prompted by well-intentioned people like Gary Marcus and so on. Some parts of this discussion were apparently prompted by the companies that focus on AI and kind of want to use the regulatory pressure to avoid other companies getting in this business. Some people like Jan LeCun said that this type of concerns are not very justified. So you can essentially find whatever point of view that you're interested in, and it's actually very difficult to look at what is out there and decide who is correct, because everybody brings the more or less valid argument. But the ultimate idea that if you read through the Hinton blogs and see what is that they are concerned about, they are concerned about the definition of the reward functions. So the idea is that if the reward function is defined in a wrong way and human is not in the loop, then bad things can happen. And that's a perfectly justified opinion. So if we have take a human out of the loop for something that is really important, and we provide the wrong reward function, the algorithm can do something that we totally not expected. So if you like the if you like the Middle Eastern tales in the whatever Thousand and One Nights and so on and so forth, there are plenty of stories about the genius that if you open the bottle with the genie and genie comes out, you have 3 wishes. However, you have to be very careful about how these wishes can be formulated, because if you formulate it suboptimally, then the genie is going to take the the easiest path and not necessarily exactly what you want. So there are multiple examples of how it can go wrong. So in some sense, the concerns about the X threat from the AI is exactly the same type of the concern. If you don't if you have a very powerful tool connected to the physical infrastructure that can affect our well-being, and if you specify the wrong reward function, bad things can happen. Notice that, of course, we are not going to solve this type of concerns by running the experiments by SPM or even material selection or theory or something like this. But the nature of the problem that we have is exactly the same. We define some form of the reward function. So here, find some form of representation for the nonlinearity. Here, as the hysteresis loops areas, here as some strange parameter of the measured Ronchigram. So these reward functions are formulated in some sense ad hoc. We cannot be sure that they are correct ones. We also cannot be sure that they are not affected by the specific measurement conditions. For example, we have some distortion in our imaging system that ensures that the maximum is in the wrong place. So we don't know that, which basically means that rather than trying to take human out of the loop completely, we need to find a different paradigm of how the human and the machine learning algorithm can work hand in hand. And it turns out that in terms of the deep kernel learning, that's eminently doable. And it is eminently doable because the whole workflow, the whole feedback loop here is actually very straightforward, and the points at which we can make an intervention are very, very clear. So let's look at this workflow one more time and see what we can do to make it happen. So obviously, when we acquire structural data or form our exploration space, that's not the point where we start, where we can make an intervention. So we can make it big or smaller, but in some sense, this is what we are given to work with. It's not what we can modify, at least for the DKL. However, the first thing that we can do is to define initial exploration targets, meaning that once we run a DKL experiment, we need to define where we are going to take the first seed measurements. And this is actually, this ends up working exceptionally well. So in some sense, we have shown that if you explore the feature space of the system, so I'll show you what it is possible to select the initial points for the decal experiment in such a way that the algorithm learns 80% of information inside the 10,000 measured points in just 30, 40 steps. What it told us is that the efficiency at which we can collect data on the real microscopes can be improved by at least a factor of 100. In fact, we cannot estimate how much it can be improved because our dummy data sets, when we pre-acquire the data, simply are too small for us to make a meaningful extrapolation. That was a super interesting result. At least we don't know how well it generalizes, but the fact that it works for several systems is already super impressive. But this is where we can define our first point of interaction. So we can define our initial exploration targets. Then we have a second point of intervention where we say what physics are we interested in. So remember that we measure spectra, we reduce the spectra to scalarizer. So this reduction comes with some control knobs. We can make a scalarizer broader if we integrate, or narrower. We can switch from scalarizer that says look at peak 1, switch to the scalarizer, look at the peak 2. So we can change the definition of the scalarizer on the fly during the experiment. And secondly, once we have our deep kernel learning workflow, we have acquisitions. We calculate the prediction and uncertainty, but we combine those to make the acquisition function. And we can choose the acquisition function, right? So if you have the upper confidence bound, it's a prediction plus something times uncertainty. If we make this something very small, then our acquisition function is greedy. We go for the brute force optimization. If our parameter is actually very large, or specifically we just reduce the contribution of the mean, that means that our policy becomes more exploratory in nature. So we can just tune these parameters. And then if we look at this whole thing, that we make a decide the next position, well, the instrument can suggest what is the next position, but we can say that, maybe there are some objects in the real space that we actually want to look at. Interestingly enough, that's kind of another difference between the imaging and difference in imaging and say molecular discoveries, is that we save more data than we use to make decisions. So we make decisions based on scalarizers, but we save the full spectrum, which basically means that at each point of the exploration in the workflow, we can say that, if I have a next step that points me to this location, I can also estimate where would my algorithm tell me to explore if I use a slightly different criteria. So for example, if I make the exploration based on the loop area and it tells me go to this location, I can also say that, if I were looking at the loop height, then the location would be here. So that kind of gives me the idea of where I want to guide my experiment. Question becomes, how are we going to monitor the process? Like, how do we know that the model learns? And it turns out, remember that the measure of how well the Gaussian process works is the predictive uncertainty. It's not a true measure. So it's what the model thinks it knows. It's not how the model prediction are different from the ground truth. So remember that generally we don't have ground truths. However, the evolution of the deep kernel learning uncertainty with time is something that we can use as the very reliable metrics of the progression of the deep kernel learning experiment. So these curves look fairly simple, but in fact, they pack a lot of information inside. So let's look at them one by one. So the first thing that you will see here is the black curve and the kind of cloud of points, the uncertainty about the black curve, sort of uncertainty of the uncertainty. you will see the blue line with some uncertainty interval, and you will see the yellow line with some uncertainty interval. So what are these? So the yellow line is what we call a complete model. So complete model is when we have all the data, and obviously we have all the data only when the data was pre-acquired. So in the real experiments, we don't have the access to the yellow line. In real measurements, we have access only to the black and blue. But what the yellow line tells us is for the optimization of the algorithms, for the optimization on the algorithm or just figuring out the metrics, it basically tells us how much the deep kernel learning model could have learned if the all data were available. So the blue line is relatively easy to understand. So the blue line is the state of the learning of the model by the end of the actual experiment. So here we have 100 experimental steps. So basically the blue line and the black line coincide at the point number 100. So that's actually what the system learned by the end of it. And now so this provides in some sense the metrics of how much we knew by the end of the experiment and how much we could have known if we had access to the full data set. So in this case, the data set would be something like 10,000 points. So you can see that yellow model has been trained on 10,000 examples, blue model has been trained on 100 examples, and the black model started from being trained on several examples, and then this is how it learns with time. So these are the indicators that we have. Now, the important thing is what does the black line and the uncertainty of the black line means. So remember that when we have the deep kernel learning model, the way that we analyze it is that we take our image patches, and for each image patch or for each object, we calculate the prediction and uncertainty. So what you see on this curve is the scenario when we don't care about the prediction, we only look at the uncertainty, and then we find the average uncertainty for all patches and the distribution of uncertainty. So in some sense, the position of the black solid line means is how the model is certain, what is the average certainty for the model for all unexplored patches in the system. And the interval around it basically tells us what is the distribution of the certainty. So is it equally uncertain for all patches, or is it the case that for some patches it is more certain and for some other patches it is less certain? So this is a little bit kind of takes a while to kind of get an intuition of what is the uncertainty of uncertainty or dispersion of uncertainty means. But ultimately, it is very simple, and it's kind of connected to how the DKL algorithm works. And then, of course, when we run the actual experiment, we run it with either one acquisition function, for example, expected improvement, or another acquisition function, which is maximum uncertainty, or a third one, which is upper confidence bound. But if we have the pre-acquired data set, we can run the deep kernel learning on this pre-acquired data set and compare the behavior for the different acquisition functions. So what can we learn from these curves? So let's start from the maximum uncertainty, because this is the simplest one to understand. So look what happens in this case. So first of all, our black curve start to fall down fairly rapidly, and then it kind of gradually saturates. It's not super fast, but reasonably fast. Secondly, the width of this black shadow around it is actually relatively small. So what does it mean? It means that in this case, we have chosen the policy where we don't try to find the high values of scalarizer. We just want to explore and find out what scalarizer corresponds to which patches. So that's a purely exploratory policy. There is no exploitation whatsoever. If we do that, then you can see that our learning is gradual, And the fact that the width of this black shadow is more or less constant it becomes very small means that the model gives equally good predictions, or at least model thinks itself that it gives equally good predictions for all the patches in the system. So comparatively, look at this acquisition function. So this is expected improvement. Expected improvement is actually a fairly greedy function. So as the result, two things happen. First of all, the predictive uncertainty across image patches is fairly broad. So what does it mean? It means that this acquisition function tries to explore only the patches where it expects to have a high return. It does not explore other patches. As the result of not exploring other patches, it has a high predictive uncertainty for that. And what's interesting is that it actually learns fairly slowly, so it doesn't go too well. Then the upper confidence bound function, that one combines the exploration and exploitation. Notice that in the beginning, it actually learns faster than the maximum uncertainty, but there are kind of jumps. But then it gets stabilized, so it doesn't want to explore anymore. It believes it already found all the interesting regions. So you can see the clear difference between not greedy exploratory policy, very greedy policy, and sort of moderately greedy policy. Okay, so that's one way to monitor it. And again, as the reminder, remember that in post-acquisition forensic, if we have pre-acquired data set, we have access to this parameter. So this is what we learned, and this is what we did not learn. In the real experiment, we will not have access to the yellow line, so we need to kind of operate based on the behavior of the black line only. So what else can we do to monitor the automated experiment? I mean, the great thing about microscopy is that microscopy shows you where the measurements are being taken, and we can correlate it by eye. And this is the example with what we see on the screen. So this is the example of the real space trajectory for these different functions. So this is expected improvement, maximum uncertainty, and this is UCB. So notice what happens, that this is the most exploratory trajectory. So interestingly enough, as the most exploratory trajectory, it started with locations here, here, and here. And then it sampled the central part where there are two layers of plasmonic particles. And generally, at some point, it kind of start to balance exploration at the edge, this region, this region. So the expected improvement trajectory and upper confidence bound trajectory, somehow they decided to focus on the edge. So the reason why it happened is because our optimization target was the intensity of the edge plasma. So interestingly enough, if we have the policy that balances the exploration target, the greedy component, and the exploitation, then, and we look for edge plasmon, we found it on the edge. If we don't have any exploration target, exploitation target, we only explore, then interesting things happen here. But notice that both the UCB and expected improvement in the beginning, for whatever reason, decided to explore this region. So I suspect that there is something there that is registered on the EEL spectrum. I just don't know what it is. But the MU did not do that. So then you can ask a question. You know what? Okay, this is great. And to some extent, in this case, we have a human eye that allows us to explore that, okay, here it goes in the edge, here it goes in the central part. But human eye is limited in terms of perception. So we can distinguish the objects on the, let's say, 2000 by 2000 point image, maybe not 5 by 5000 images. Electron microscope can easily create images which would be 32 by 32,000 points. So human eye would not be enough to recognize the details. Is there a way to represent the structural variability in the system better? And the answer is yes, and that's exactly the reason why a week ago we had a lecture about the variational autoencoders. Because basically what the variational autoencoder does, it tries to find the factors of variability in the system and order them in a way that makes sense in order to create this latent representation. But the thing is that we have access to the whole image before we start the experiment, which means that we have access to all the image patches. And that in turn means that we can take all the image patches, put it in the variational autoencoder, and we get to choose whether we use the simple one or we use the invariances to accommodate for rotations or shifts. And once we have it, we have access to the feature space of the system. So the feature space in this case is 3 elements. One element is the latent representation. So this is what are the simple representations of the structure. And you can clearly see that they kind of make sense. So these are the edges, these are tilted edges, these are edges tilted in the opposite direction. So this, so these are kind of sharp edges and so on and so forth. So this is, of course, the latent representation in two-dimensional space, but we can always use the high dimensional one. It's just not as convenient to visualize them. Second element, so this gives us the disentanglement of the representation of the data, and that defines what are the microstructure elements are. So this is our latent distribution. So latent distribution basically tells us at which densities are they pronounced. So what is their densities? So you can see that here the latent distribution maximum corresponds to this type of features. So these are edges. And then, of course, we also have we can also map the latent variables back on the original image, which basically gives us the idea of kind of information where do the elements represented by this combination of two latent variables, where they're sitting in the real space. You can see that the angle distribution is more or less predictive. So these are primarily the angles corresponding to rotation of the edge features. Sorry, these are the angles, my bad. So these are the latent 1 and latent 2 variable. For some of them, it's fairly straightforward to understand what it is. So latent 1 variable is low when there are no particles, have a specific value when we have one layer of particle, have a different value when we have two values of particle. So this one is relatively straightforward, and it on the latent representation, that means transition from this part where the latent one is small to this one where the latent is large. So the second one is a little bit more complex and corresponds to the final details. So typically one latent variable focuses on obvious factor of variation, and the second one focuses on the less obvious factor of variation. But once we have this, I mean, in this case, it's visible because we can look at these images and kind of have the human eye interpretation. But we can create this feature space for arbitrary size of the image. It's just the computational complexity that becomes an issue. And if we have it to the arbitrary size of the image, then we can represent our automated experiment as the trajectory in this feature space. So in this case, I don't have a timestamp. I've just shown the trajectories corresponding to the expected improvement, maximum uncertainty, and UCB. But you can see that the different algorithms sample different part of the feature space of the system. So for example, the maximum uncertainty clearly samples this part of the feature space, and the UCB and expected improvement do not. They tend to be stuck here. So if we compare these observations to this data set, we can clearly see that this is the features that maximum uncertainty sampled, and this is where they are in the feature space of the system. And they correspond to this type of objects. At the same time, I'm not certain, but it looks like that these features correspond to whatever happens in this case. And this is this part of the latent space of the system. So in some sense, we get the several monitoring tools that allow us to observe how the model learns. So this is the uncertainty behavior or the learning curve. We get the tool that allows us to monitor the real space progression. And then we get a learning tool that allows us to monitor the progression and the feature space of the system, what features are interesting, what are not. And on all of those, we can make an intervention because, for example, if I observe the automated experiment, let's say after a while, I can say, you know what, I want you to start measuring from this location. I can just manually define several measurement points. Or I can say that, you know what, you're exploring the feature space of this system like this. For the time being, you are stuck on this feature, whatever it is. I want you to explore the features sitting here and here. So all of this provide both the monitoring function and they provide the intervention functions. I, of course, cannot intervene on this curve. This is pure monitoring. I cannot tell my algorithm to learn faster. What I can do, however, is I can tune the policies and say that I want you to explore, to be more exploratory, or I want to be more exploitative. So either look for broader variety of behaviors, or, you know, I'm running out of time, I need to stop running the experiment, go greedy and find me the regions with the best response. However, once we let's make a step back and look at the big picture of the whole process. And the big picture becomes very, very interesting and somewhat unexpected, because normally we run the scientific tools, for example, I mean, microscopes, obviously, but pretty much any other tool, it can be microscope, it can be synthesis and characterization tool, is that the human does everything. So human executes the basic commands, and human gets access to the imaging and spectral data. So there is always this feedback when we observe the data and we make decisions what to do next based on the data. In microscope case, this has to be done very, very fast. So we just work with the microscope in real-time regime. If we run things in the lab, then the feedbacks are slower, right? So we get the sample, we go to X-ray, we go to do the Raman, whatever. But the idea is always the same. Human does it's an interactive process when the human executes decisions and plans the experiment. At least for the microscope, and that will actually generalize to other tools, we have now a slightly different approach. So now we have the machine learning agent that can execute the primitive commands. And this is the machine learning agent that does some form of analysis of the imaging and spectral data. So this is our deep kernel learning loop. What the human does is that human, of course, can do the direct intervention if necessary, but most of the time, human observes what the machine learning agent is doing. If the machine learning does operations at the human rate, we can observe it kind of action by action, but electron microscope is much faster than human. So, and even scanning probe microscope is much faster than human. So in many cases, we will observe not the single operation by the machine learning agent, but basically the trace of multiple operations. And if so, then we get an opportunity to intervene based on the rewards or based on policies. So we don't run the instrument ourselves. We tune the behavior of machine learning agent where we observe the aggregated evolution of the knowledge on the system, our learning curves, or our trajectories, or our features our trajectories in the feature space. And as the result, we decide how to affect the behavior of machine learning agent rather than run things ourselves. And we long thought that if we have the automated microscopy, it would be something similar to kind of going from driving the whatever Honda to driving Lamborghini. But what turns out is that that's underestimating the difference. So practically, it's more like we were riding a horse to driving a car. So both are used for getting from point A to point B, but the nature of controls is very different. So switching from the human-driven microscopy to kind of human-in-the-loop machine learning operation is the same type of change. So does it realize? Let me show you one example of when we realize this human-in-the-loop control. So this is the example done at Oak Ridge when we work with them on building the workflow, and Yongtao, Arpan, and Rama operationalized it. So in this case, this is a very simple example when we have the same type of workflow. When we start with the image, we define our patches, we define what is that we're interested in, and then we kind of realize the human in the loop workflow by simply a person saying that I am interested in this response and I'm not interested in this response. So the way it is done is that rather than going for the complex tuning, you simply provide the upward and downward of what you observe. And then once you do that, you have the instrument that actually learns what type of behaviors the human is actually interested in. So in this case, some things are human in the loop part, some of it is the classical Bayesian optimization, some of which is the implementation of the microscope. So let's see. So this is how it actually will look like. So you can see that the microscope is acquiring data. Human needs to provide the information of about upvote to downvote. So if the human didn't like it, then you just press enter. If you like what you have seen, then you say, I like it or I like it a lot. And eventually the instrument learns to find things in the image that you think are important. So this is the example of this, in some sense, simplest human in the loop workflows, but they can be made much more complicated, as I've shown you for the DKL example. So can we make it more complex than that? So notice that, and kind of going back to the beginning of this lecture, the most difficult thing that we have to deal with now is the fact that our reward functions are very scarce, and we don't necessarily know how they connect to the long-term objectives of the experiment. So I would even go as far as to say that if the reward functions were available in full, then we would not need any machine learning whatsoever. So all we will need to do is to use the existing optimization algorithms, and kind of you don't hear the word optimization as much as you hear large language models was not, but optimization is very well established field. It's also a very powerful field. It's also the field which is much more relevant to experimental sciences than, let's say, large language models. The problem is that we never know the reward functions. We can approximate them, and sometimes we can approximate them very well. But generally, the relationship between the reward function that can be achieved in the experiment and long-term objective of the whole project becomes very unclear. So in this case, we know that if we run the individual tools and we have well-defined rewards, we can run the myopic workflows like the one that I've shown you. And that's, I mean, we are obviously in the beginning, but it feels now that we're in the end of the beginning. So we have the theory for these projects, we have the algorithms that work. So the DKL is one of them, but there are other ways to solve similar problems. So they exist. It can be so anything that gives prediction and uncertainty can work, from pins to the bandits to contextual bandits to what's not. So here we're definitely in the end of the beginning. So it's a matter of deployment, developing the right reward functions, and so on and so forth. If we talk about the non-myopic workflows, when the rewards are available only at the end of the day, that's complicated. So that becomes a stochastic optimization and reinforcement learning algorithms. The algorithms exist. The reason why it is difficult to use them is because we simply don't have access to the required number of repetitions that the simple reinforcement learning algorithms require. Nonetheless, it's doable, and there are ways to do the initialization based on the human heuristic. The difficult part becomes on how do we create the objectives. So maybe this is the part where the large language models can be useful, maybe not, but there are ways to learn something. There are clearly directions where it can go. And obviously in the future, we think that we are going to transition from the simple workflow simple one-step optimization to much more complex workflows when we do everything in this in the loop, from image optimization to spectroscopy to exploring outliers to exploring specific scientific hypotheses. So for microscopy, it's definitely doable. For material synthesis, it's become more complicated, primarily because the rewards are more heterogeneous and the times are longer. Now, in the end of this presentation, I have kind of provided the summary of some of the keywords that are important to understand what we have been doing. But rather than going through this table, let's look at the practical examples of how this type of workflows are realized. So I have put the several examples on the GitHub. So let me share with you one of them and just look at the kind of conventional example from Maxim of how the DKL for the discovering the plasmonic structures look like. So what you see here, you've already seen it several times. So this is the install of the GPAX and Atom AI. So the Atom AI is the library that we are going to use only to prepare the input data, meaning the image patches and the spectra. It can be done in many other ways. This one is just convenient. So these are the installs. These are some checks and library imports. So what are we going to have access to? We are going to have access to the electron microscopy data, which is just the EELS dataset. So in this particular case, you will not have to deal with anything related to how to curate and parse the data. It's already been transformed into the NumPy version, and it has been uploaded just to make the life convenient. So what you will have to do is to run this. What you will have to do is to just upload it, and you will have access to the several data objects. So load file creates a dictionary. So the dictionary contains the image itself. So the image is 62 by 75 pixels. So notice that this is kind of not a true image. This is the image that we formed out of EELS data itself. So we don't have to deal with the registration problem. We have the spectrum image. So spectrum image is 62 by 75. And this is 14, almost 1500. This is the number of the energy pixels. So the energy axis basically tells us that this is in pixels. This will give us the true values of the energy. Scale is just scale. It's just a scalar. So then what we do is we give names to these objects so that we know where they are stored. And then we start our process. So notice that the first step in our process is find the descriptors. So in this particular case, we say the descriptor is 16 by 16 window. So what these functions are doing is basically do the following. They take the image. So this is our image. We say that with step one, so every pixel, we basically create a grid of points on which correspond to the center of the patches. So when we have these coordinate objects and use this get coordinate grid, essentially it just creates the grid of points from which we are going to take patches and spectra. And then, as you can imagine, this function extracts patches and spectra. All it does, it takes our data set. So it takes the spectral image object, which is where our spectrum are. It takes the image object, which is images. It takes these coordinates. And basically what it does, it creates the pairs of patches and spectra. So that's all there is to that. So I can show you how it looks like. So if you look at the output, it tells you the shape of the features and shape of the targets. So notice that 2800 is the number of the patches and spectra. 16 by 16 is the size of the patch. So this is where this came from. 93 is because we use the average pooling. So when we have the spectrum that has 1500 points, that's way too much. So once we average pool it, then we basically make it much smaller. And it's very easy to see what happens inside. So we can look at some specific patch, and let's say we can look at the patch number. Oops, sorry for that. So we can look at the patch number 12. So it's going to be, you can clearly see that we are here between the four squares. If you look at the patch number 34, so this is a different location. So this is how our patches look like. In microscope, they would be just sampled from the instrument. Here they're pre-stored. So we can also look at the targets. For example, if we want to look at the spectra, so oops, sorry for that. So this is how the spectrum will look like. So this is the spectrum at the same location. So of course I can show both of them, but in this case we've chosen them to be large. So I can look at kind of across our data set and see how the spectra look like and how the images look like. So this is the access to the data. So this is the part where our pre-acquired data comes into play. Realistically, we have access to the microscope. So the features are available before. Targets will have to be discovered one by one. That's what active learning is for. So then the next thing that we need to do is we normalize them. So the next thing we need to do is to define the scalarizer. So as I said, defining the scalarizer in some sense is the most difficult scientifically when it comes to this type of work, because scalarizer should represent what is that about the system that we are interested in. And generally, the easiest way to define the scalarizer is to simply find the maximum position of the maximum. So that's an easy one. It doesn't have to be this way. For example, I can fit this curve by the three Gaussian peaks, and I want to choose the intensity of the second one as my measure of physical interest. So this is where the domain-specific physical knowledge comes into play. And then then the way I proceed is, since this is a training notebook, I can simply define the scalarizers as a ground truth. So this is how it looks like. So ultimately, this is what I want to discover. In this notebook, I have access to it because it's based on the pre-acquired data set. Practically, if I run it on the instrument, then I will have access only to specific locations where I already have taken the data. So it's very important to kind of have this dichotomy in your mind between what you know and you use for comparison and benchmarking the algorithm versus what the algorithm knows. So it's always important to kind of keep it in mind. But let's see how the algorithm works, and let's start with the reconstruction from the partial data. So what we do in this case is a very simple scenario. So imagine that we say that we have access to all structural data, and we have access to the spectral data from this part of the image, so to the left of the line, but we don't have access to the spectral data on the right of the line. So the realistic scenario can be that we have all structural data, and then we're acquiring the spectral data in the grid mode, and we kind of do it in the scanning regime. So we measure here, and then based on it, we want to reconstruct what happens here, where we haven't seen it. So see what happens. So we train our deep kernel learning model like this. So this is roughly the same way how we've done it before. And this is how the prediction and uncertainty look like. So the result is actually super interesting. So first of all, we need to compare it to the ground truth. So ground truth shows that there is a bright features here. There are bright features here. So these are our H plasmons. There are something going on inside this cracks between the particles. See what happens if we run the deep kernel learning algorithm where we train the model based on this part and we make a prediction for everything else. So first of all, notice that it made a prediction of the high scalarizer in the unseen part of this hole. That makes perfect sense, right? Because what's going on the left is kind of similar to what goes on the right. That's not a big surprise. But notice that it also was able to predict the high intensity of the plasmon on the edge of this particle raft. So why did it do this? Did it because it used this one as an example. So there was a high intensity here. It decided that this edge is very similar to this edge. But the most interesting part is that notice that the DKL uncertainty is actually high here. So basically what it means is that once we trained it on this part of the image, there are no objects here that look like this empty space over here, which means that the trained DKL model said that this region has high uncertainty, and I'm not confident about the predictions on this part. It interestingly also recognized, it's a little bit more subtle, but it's still very visible, that it also predicted the high uncertainties in these locations in here. So why did it do that? It did so because here the particles are oriented in the roughly this direction. Here they're tilted, which means that the structural building blocks here and here are not the same, which means that the model interprets it as the high uncertainty. So basically, it takes a little bit of time to kind of look what goes on here, what is predicted, and what is postulated to be uncertain. But in the end, we can see that actually it makes perfect sense. So we can also visualize the latent space. So latent space in this case is relatively straightforward. So it's just two-dimensional. Some of these elements is something that we expect to see. Some of these elements is something unusual. So we don't know what this contrast suggestive of, but that means that we actually see something about our material. And then the final part here is the active learning. So we proceed in a very simple way. So we define the, let's start with the 0.02% of the grid data point as the training. So we choose 5 points where we measure scalarizer. And then we define our exploration loop. So by now, you have already seen how this type of loops are defined. So we define the number of exploration steps. We train our model. We feed the model to all data. We calculate the acquisition function. We choose the next location based on the acquisition function. And this is the place where we can introduce the penalty in order to force the algorithm to go around and explore more. So we can define the next measurement point, then we plot the results. So see what happens, how it actually goes on. So this is where we start. So this is our acquisition function values after just 5 seed points. This is where we take the first measurement. So we retrain the model, we get the acquisition function. This is our second model measurement. This is our third measurement. This is our fourth measurement. So you can see that once we are going through this exploratory pathways, we keep exploring different locations, which is actually super good. Then after a while, let me see, where is this? So after a while, you can see that our acquisition functions actually start to converge to what we want it to be. So in this case, we use a fairly, we want to find the maximum of the behavior. So this is the end. So this is how the exploratory trajectory would look like. So notice that in the beginning, we have explored the points where there was a large uncertainty, which are not equivalent to what we train on. And then after a while, we found that the maximum intensity of the plasmon is concentrated in the locations with the close to this edge and this edge, which is actually not bad. And if we compare it to the ground truth, you can see that we actually discovered the edge plasmons remarkably well. So let me show you one more notebook. We are not going to go through it in detail, but just kind of to make sure that you have access to it and you can play with this. So this is a much bigger version of this notebook, which provides a many more scenarios about how the reconstruction will look like if we start from the 10 locations and so on and so forth. So 10%, 3%, 1%, and the active learning. So it should run and it should allow you to observe the evolution of the active learning process depending on how many steps you want to go. So this is the example when we start from 1/10 of the percent of the sampling point, and then our active learning identifies this region and this region for a different scalarizing function. So this notebook has to be fairly self-explanatory, but it will take also a while to go through and kind of understand the logic. And then the final notebook that I want to mention, which you probably have to download from the GitHub, because at least it tells me for the time being is that it's too large to visualize, is the notebook that realizes the human in the loop interventions. So again, follow the logic. So it describes how you import the data, how you create the scalarizer, how you train the model, how you run the active experiment, how you create the forensic analysis, and basically guides you through how the DKL learning curves looks like for different scenarios, how the acquisition functions look like, how the discovery look like, and so on and so forth. So it makes sense to go through this one in detail if and only if you are interested in trying to run it on your own instrument. So that can be fairly complicated. And as I mentioned, this particular notebooks will work for any imaging and spectroscopy methods, but they would be less useful for things like microstructure optimization or materials discovery. Those will require different settings. So let's stop at this point, and I would be happy to take questions.